Good morning.
Good morning. So I've got some slides to go through. I'll do a quick screen share. Okay. Can you guys see that?
Yes. Reflective proof theory.
Hang on a second. Can you say that again?
Reflective proof theory.
Oh, okay. Sorry. All right. Yeah. That's right. Okay. So I'm going to talk a little bit about an algorithm for generating a proof theory from a set of rewrite rules. So this is an extension of the ladle idea from just formulae and giving models of formulae to giving proofs. I'm not giving an interpretation of the proofs, just giving the actual proof objects. So it's another sort of whole step towards progress in terms of ladle. So we start with a set of rewrite rules, and we insist that these are interactive, and I'll say what interactive means in just a minute, but we insist that that these are interactive rewrite rules. And what we're going to do is to derive a proof theory that enjoys a cut elimination property. And that cut elimination property is so closely tied, so perfectly aligned with the rewrite rules, that cut elimination is exactly mirrors the rewrite rules. And so in this way, we're going to get a Curry-Howard correspondence. So Curry-Howard is this correspondence between types and formulae and proofs and programs. So this is the proof and program part of the Curry-Howard. The types and formulae part I've been talking about for quite some time. In fact, let me just review that. So we're gonna derive the formulae from a combination of two monads together with a distributive law, and that's how I usually talk about ladle. I don't normally talk about the proof theory side of it. So one of the monads, which we will call T, corresponds to the terms of the term rewrite system. So it's effectively the Levere theory corresponding to the terms of the term rewrite system. In the case of a nominal theory, it would be a nominal Levere theory. And the other theory is going to correspond to a collection, a theory of collections used to collect terms. So essentially what we'll do is we'll build a combination of the collections plus the terms, which can be seen as all words in C and T, in the alphabet C and T. And the interpretation of any such word we will give as a C composed with T. So you could have, you know, TCT, TTCT as a word, right? And that represents that combination of those two monads. And I'm going to show, and you can easily see that if you have the monad laws and the distributive law, you can take any such word and turn it, reduce it down to just CT. And what that means is that, you know, you're interpreting these formulae into as collections of terms. So that's that kind of semantics is that enjoys this property is called realizability, because what we're saying is that every formula has a meaning as a collection of terms that give rise or witness to that formula. So that's the model theoretic side of this. And now I'm going to extend that to proofs. So the proof that we're going to talk about is derived by modifying the rewrite rules. Now, to say that the rewrite rules are interactive without loss of generality, that means that all the rules are of the form K of T1, T2 rewrites to some T3, where K is some term constructor for the terms that we are rewriting. So an example would be in beta reduction for the lambda calculus, K is the apply operator, and T1 is some lambda term, and T2 is some lambda term. So when we apply some lambda term to another lambda term, if T1 is of the form an abstraction, then beta reduction will rewrite by substituting T2 for the bound variable in the abstraction. And that's how that conforms to this this shape. The COM rule for the pi calculus or the row calculus has this shape. So K is par, T1 is some pi term or some row term, and T2 is some pi term or row term. And you know, in the case that T1 is a forward comprehension and T2 is an output, then you'll get the COM rule applying. So those are some examples of interactive rewrite rules. They always have to have, you know, some constructor K that has at least two, takes at least two arguments. And then the rewrite rule will take, you know, this binary term over to some other term. And now what we're going to do is we're going to modify those rules so that we get a zero array term. R represents the catalyst for reduction. And so you can see that since K is binary, we're all we're doing is we're taking the result of K of T1 and T2 and using the first argument of K, and then R, which is also a T. And then we're going to say that change every rewrite rule of the first form into a rule of this form. And that allows us, R is basically the fuel, or you could think of it as like a token that is necessary to have to run the rewrite rule that we were talking about. So this is clearly closely related to cost accounting because R is essentially plays the role of flow or phlogiston in the R chain architecture. Okay, so let me just stop there and make sure that everyone has been following along so far. Does this make sense?
Yeah, I sort of have an idea where you're going, Greg, but I can't say. I'll have to watch this a couple of more times
Okay,
before.
yeah, understood. Understood. Yeah, I'm moving rather rapidly just because I just want to make this a quick update, uh, but it'll make more sense in a minute. So I'm going to give an example. So since we have this construction, we can now build our proof rules. And just to give some interpretation, some intuition, forming a K without an R constitutes a suspension of computation. And what it does is allows K to be a data structure. So reifying the computation embodied in the rewrite rule. So we basically, what we said, like in the case of lambdas, we modified beta reduction to take this additional catalyst R. And without the catalyst, the application constructor becomes a data structure. It has everything you need to do beta reduction, but you can't do it because you don't have the R to enable that reduction. Or in the same with COM. You have your PAR of a for comprehension and an output, but you can't run it because you don't have an R. So you're suspending the computation, but that suspension has all the data in there that you would need to actually perform a rewrite. Now, your K is not really a data structure unless you have a means to get the data out. So we introduce another term, par of U1, U2, to extract the data. So we're enriching the rewrite system with two things. One is that we're modifying the rewrite rules to take a token, some resource constraint, and we're adding the par to extract the data. And so now we can specify the proof rules. So there's a proof rule for every collection constructor. There's a proof rule for all the term constructors, except the ones that form the left-hand sides of these rewrite rules, which are typically called red X's. So in that case, there are two proof rules. One that supplies the reduction catalyst R and one that does not. The one that does supply R are called cuts, and the ones that do not supply R are called tensors. And additionally, there's a proof rule to form a par term and a proof rule to cut a par with a tensor. So this is an algorithm. I've just now specified exactly all the proof rules and how they're generated. And it is immediate from the way I've done this to show that if you build a proof that uses a cut, you can build a variant of that proof where you replace the use of the cut with the right-hand side of the rewrite rule associated with the cut. And so what that shows is that you are able to transform every proof that has the use of a cut into a proof that doesn't use the cut. So every proof theory formed in this way enjoys a cut elimination property. And the cut elimination property corresponds exactly and precisely to the rewrite rules by design, by construction. So effectively, we've now given a proof theory that enjoys the Curry-Howard property. But let's rather than be so abstract, let's show how this works in practice. So SKI is a simple rewrite system that is Turing complete. We have a notion of a term. That's our sort. S, K, and I are all terms, and then forming collections of terms using intentional sets or extensional sets is also a term. And then R is also a term, as we've said. Here I factored it slightly differently, so it's a context rather than a term, and you can make it a term by just simply making it making the application filled in with an R be your R. So that those two are interchangeable presentations. And then we have application, allows you to form term, giving two terms, you pair them up, and that's an application. We also have union, right? Because that's the collection constructor. So since T really represents collections of terms, then you can always take two collections of terms and union them together and get another collection of terms. And then we enrich the theory with our pars. So there's a par sigma and a par kappa, and the sigma and the kappa correspond to the rewrite rules. So sigma is the S rule for SKI, and kappa is the R rule. Sorry, the K rule for SKI, and then identity is just the identity. So as long as you have this R thing, you can run the normal S rule as long as you have the R, which basically distributes Z to X and Y, right? And then kill just kills Y off. That's the K operator. And then it's easy to, so now our interpretation function combines call with term combined with pars, and then it takes that over to composing collection with the term combined with pars. The term combined with pars is just literally enriching the grammar with the par constructors. All right, and so that's how we've enriched our language with the term constructors, as I said. And then here are the types that are auto-generated. So so you have just the usual. We start with whatever sorts are available from the Levere theory. That's T in this case. Then we can form an arrow type. We can form the tensor, which is for the sigma kappa, the par, and then there's a type for each of the terms, plus the collections, plus forming R, and then application and union. So that's all the types that we get. And now the proof rules look like this. So essentially, as I said before, you're going to form an S rewrite rule. You're going to take the S rewrite rule and not supply the R, and you're going to form the S rewrite rule and supply the R. So that's here, right here. So this is the tensor, this is the cut, and I'm only giving you some samples. Right. So this is the normal S rewrite rule, but there's no R. This is the S rewrite rule with the R. And then there's a similar one for the construction of the par. And then the interesting one is when you cut a tensor against the par. So now we have we've got a proof for a par, and we've got a proof for a tensor, and then we extract them out, right? So the X goes with the X, the Y goes with the Y, etc. So we form that, and then we make an S around that. So it's basically zippering S along these two, and you'll note that that because of the way this is constructed, all computations will terminate with whatever property M holding, and M we get to, program in. So it could be deadlock freedom, it could be, just basic termination. Any of these things, M will be the property that happens at the end of a cut elimination procedure. When the proof is cut free, then M will hold. And we know that that as long as everything is well typed, then the property of removing all the cuts is terminating. So that's an example of how to run this algorithm on the SKI term language. So I just showed you how to do this for something that's Turing complete. As you can see, the whole thing is finite, easily generable. We can do the same thing for lambda, not SKI, the one with abstraction. We can do the same thing for rho or pi, and it all hinges on this two things that we've done, which is the introduction of the catalyst makes it possible to suspend and reify computation. And then the par makes it possible to unpack and modify the reified computations. And then the cut rules, especially the par tensor cut, make it possible to reflect reified computations back into running computations. So essentially what we're saying is that adding the catalyst gives us this ability to reify. It's basically the system becomes reflective, and the reflective piece of it is what makes it possible to enjoy this cut elimination property. And so now, even though there's a lot of jargon here, what we've done is we've built a type system and proof system, proof theory for the rewrite rules that enjoys realizability, at least for the formulae, and Curry-Howard. And in subsequent work, we'll show how to realize the proofs, and that will complete the whole program. This is already having some impact on our chain, because from this I have been able to derive an idea that would allow us to not do the replay for validating. So verifying so when a block is proposed, simply giving a proof of that a particular deployment will result in a tree of comms. So essentially the way that works is you can build a tree of comms. That's the comm events. This is a tree of comm events. And then there's a corresponding tree of R space deltas. And then all you have to do is to check. So the tree of R space deltas is the proof object, essentially. And the tree of comm events is essentially a kind of specification of the formula. And then all you have to do is to verify that the proof that the tree of comm events matches the tree of R space deltas. And you can organize this in this nice way so that there's this is much less uh, computation than doing the replay of the deployment. Currently, to replay the deployment, not only do you have to run the deployment, but you also have to then check that the deployment matched certain criteria. So that makes it more expensive to run. With this proof verification thing, you're doing a lot less work, and particularly you never hit RSpace again. So you only hit RSpace the first time, and you don't do RSpace for the proof verification, which should give us a considerable speed up, like a whole bunch. And all of this whole idea, this whole architecture derives from this proof theory. So this is a fairly significant win. So it's been kind of a holy grail to give proof theories that automatically enjoy the cut elimination. So we've done that, and then we've extracted from this a way to significantly speed up the execution of RChain. So that's, there's still a lot of work to do, but this is essentially the shape of the work that's been going on over the last, I guess, about 2 or 3 weeks. It's sort of where the ladle stuff really begins to pay off for part of RChain, and then there's more to this because once you have this logic, of course, you can do all kinds of things like check the behavioral type style properties that the logic provides. But now we do this for any interactive rewrite system, not just Rho. You can do it for any interactive rewrite system. All right, I'll stop there, see if there are any questions, or if people, just get people's thoughts.
I was going to add, there's a video out on YouTube. You had mentioned about the SKI and doing computation with SKI. I was trying to find it. Is there another name or title for doing that computation with SKI by chance? Anyways, yeah, there's if you
oh, sorry, I accidentally muted myself. Yeah, so
okay.
it's called combinatory algebra. There's lots. There's just like lots and lots and lots and lots of literature about SKI.
Yeah, and it's I wasn't aware of it until several months ago, and I watched a video of a guy. He did all the you can do math and computation with those 3 letters, and it was kind of neat to see. So
Yeah.
if I come across it, I'll share it with everyone in the Discord channel.
Sure. There's a nice presentation. I think Smullian does it, where he describes them in terms of a bird metaphor. But anyway, yeah. So we just used SKI because it's one of the simplest systems, so we don't have to deal with nominal phenomena and a bunch of other stuff, right? It's very, very simple. And we're able to just it's the first test case to try the algorithm, and the algorithm obviously works for SKI. And the next one we'll do is the row combinators. So we'll.
Greg, you said one thing about comparing the RSpace deltas to comma vent paths. I think was the way you put it.
It was trees. So you get a tree of comma events, right? And that would be that would represent the execution of a particular deployment. And you get a tree of RSpace deltas.
Yeah, the RSpace deltas what by that you mean the differences between
You have R space. You have R space in one state, and then you have R space in another state. So the delta is the change in R space from the first state to the second state.
Okay, I was thinking that's what you meant. And you mean from one state to another, one step of the blockchain?
I mean, it's that one step of the. I mean, the blocks contain lots and lots of deltas to R space. So one step of a deployment, right? One step of a row lang program will result in a change in R space.
Okay, that helps. One step of a program, yes.
Right, and so since the only kind of steps you can get are COM events, that's what's going on, right? So you just compare the tree of COM events that because the program can contain concurrency, it's going to be a tree, right? So you've got some kickoff event, or possibly multiple kickoff events, but at least one. And then because there's concurrency, then after that kickoff event, you may have multiple COM events at the next level down, and then each of them may have multiple COM events below them. So there's some tree that corresponds to the execution of a row-lang program. And each one of those COM events corresponds to a delta in R space. And and then the only thing you have to do is to make sure that, if there's any kind of delta that involves, the running of a function, as opposed to just doing a COM event, you have to run that function. Because you have to compare the inputs and the outputs. Because you can't let a validator lie about the execution of a function. Right? If it were all just pure row, the validator can't lie, because there's no change that isn't recorded in the R space deltas. Right? You can exactly track all, like the values have to exactly match. The only time where the values wouldn't exactly match is if, like you input a number n on a channel and you output f of n on some other channel. So in that particular case, you have to compute f of n. But you only have to, provide the name of the function, and the lookup for the function will be the same, right? The functions have to resolve to the same things in any two deploy, nodes, and so you just run the function again. So you still have to run any sort of arithmetic or anything that looks like a function, that is an enrichment of row line, from row line, from pure row calculus to row line. But that's still, you can show that as long as those functions don't require touching any state, right? As long as they're essentially restful functions, then you never have to go to R space. You never have to go to the database, which means that the thing is going to be considerably faster. You never do any of that I/O. The whole thing can stay. The whole check can stay in memory, and that will dramatically speed up the execution, and it will still be secure. So essentially, what you're doing is, when you post the block, you're posting a cryptographic proof that this is, that this computation is the one to take. And so each validator only has to verify the proof and then update their RSpace accordingly. And then you're done. You don't have to run RSpace. You just do the RSpace update, boom, in one fell swoop. And that's I mean, I'm not going to suggest that we do that change before Mercury, but it is because I want to write down the proof so that everyone is satisfied. Mike and I had a good conversation yesterday about it. But you know, I think everyone wants to be satisfied that that works. So that you know, if when we move over to this more optimized thing, we don't lose any security. So I don't know. I'm pretty excited about this. I think we sort of solved a long-standing problem, and it generates a really powerful application to the blockchain, and basically automates a big chunk of what constitutes blockchain for a wide variety of languages. What it says is that this whole idea of constraining compute with resources gives rise to a natural proof theory. Any other questions? Awesome. Well, thanks, folks. Go ahead.
Thank you, Greg, for the presentation. We enjoyed it. Thank you.
Oh, thank you.
Thanks,
All right.
Greg.
Sure. You guys have a good Columbus Day.
Oh, thank you. You as well.
All right. Ciao, ciao.
Bye.